Hi everyone, welcome to physics. I'm going to, in this lecture, introduce you to the idea of angular kinematics, look at rotating objects. So far we haven't considered rotation. We've treated objects as particles. We just began to touch on that idea when we introduced the concept of center of mass in the last unit. So in today's bell work, I want you to consider this rolling wheel. So as it rolls across the tabletop, rolls without slipping, I want you to use the language we've already learned in this class to describe the physics of this motion. So things like velocity, position, acceleration, kinetic energy, potential energy, center of mass, momentum, any other terms you can think of to describe how this thing moves. See what you can do. Ready, go. So among other things, in your discussion or your examination of the rolling wheel, you should realize that the wheel is doing a combination of two different types of motion at the same time. In one sense, the wheel is translating, meaning that it moves in a straight line in one direction. At the same time, the wheel is also rotating, or has an angular motion to it as well. So rolling is a combination of the angular rotating motion and the linear translational motion happening at the same time. Let's take a closer look at the vectors that are involved. All right, so here we are beginning the next chapter of the textbook, chapter 8. Our unit will be divided up between chapters 8 and 9. And chapter 8 is all about rotational kinematics. So just like when we studied linear kinematics, we're going to limit ourselves to just how objects move, not why. And we're going to make a second limitation by limiting ourselves to rigid bodies, so objects that don't squish or deform. So let's think about our bell work today, and we'll be on a roll then. So we said that the rolling bicycle wheel was experiencing two different types of motion at the same time. So if we're to draw the wheel here, here's its center. In one sense, the wheel is rotating. And in a rotating object, if I were to pick some different points on that object, those points are experiencing circular motion as the object rotates. And so different particles on the wheel, say at the edges of the wheel, have tangential velocities. So this would be pure rotation. And if we're going to roll, we're going to both rotate and translate at the same time. So I have to add to that translational motion. So suppose the wheel is rotating, but at the same time it's also moving to the right. So the pure translation looks like every particle of the wave, the center, the top, and the bottom of the wheel, all traveling to the right like this. So this would be translation. Now if I put both types of motion together, I end up with what we think of as rolling. We'll say rolling without slipping. This is not sliding along the ground. Then I have to add my vectors together. So if I were to pick some different points, such as, say, the top of the wheel, where I have a v vector and another v vector, the top of the wheel is going to have an overall motion of 2v to the right. The middle of the wheel, in the rotating case, isn't moving, and translating it is, so it will, adding those two vectors together, it will have a velocity to the right of v. And the bottom of the wheel is most interesting of all because the two vectors are equal and opposite. So the point right at the bottom of the wheel has a velocity equal to 0. And we already knew this because we knew that as a wheel rolls on the ground, static friction is the type of friction that causes it to grip the ground because that particle is at rest. So what we're going to start off with in this unit is considering the physics of how to describe rotation, pure rotation. And then later on we'll put it together with translation to look at more complex motion like rolling. So let's begin trying to lay out some basic ideas in angular kinematics. So angular means rotational because we are rotating through an angle, as we will see. So let's try to generalize. Let's imagine some sort of a rigid body, and it could be just about anything. So I'll just draw this sort of nebulous shaped object, and we'll place it on a coordinate system. So this is a three-dimensional object, So we'll have an X, Y, and Z axis. X, Y, and Z, something like this. And I could rotate this object however I like, but let's say we rotate it, we're going to rotate it about the Z axis. So Z is going to form the axis of rotation. So this object is rigid, so all parts of this object are going to rotate about the axis at the same time. So in kinematics, one thing we learned we want to talk about is where an object is located. So we had position, and in linear kinematics we had a linear position, which we use the variable x for. Well, now we have an angular position that describes how this object is oriented at one moment in time. And so we're going to use the variable theta, since we often use theta to represent an angle, to represent our angular position. The unit for theta is going to be radians. So we'll be measuring in radians rather than degrees. So now we got to get used to switching our calculator back to radian mode. So to show the angular position of this object, remember position is somewhat arbitrary. We get to pick where the 0 position is on the x-axis. We'll get to do the same thing with our angular position. So we're going to draw an arbitrary line, a line that's perpendicular to the axis of rotation. And this is going to be our reference line. It's going to describe where this object is as it rotates at a given angle. So it's a little hard to see this in 3D, so what I'm going to do is rotate the picture, and imagine we were to look at this from an above view perspective. So now we're seeing this in just a two-dimensional drawing. So in a two-dimensional slice, maybe we're looking down the z direction, and so we see x and y, something like this, and we've got our blob object here, and it's going to be rotating about the z-axis, something like this. As we look at it from above. Okay. So if I'm going to draw my reference line, I have a reference line starting here at the z-axis, perpendicular to the z-axis. It would look something like this. So here's my reference line. And from this line of reference, I can talk about the angular position of the object. And just like we did with polar angles, we're going to be measuring our angular position relative to the x-axis. So in this case, I look at how many radians this makes from the x direction. So this would be my angular position theta. So in this case, yeah, it's a pretty small angle. So in degrees, maybe about 30 degrees. In radians, something, I don't know, like a quarter of a radian or something. So suppose that this thing continues to rotate. This reference line is going to move with the rigid rotating body. It's not going to stay in the same spot. So sometime later, the reference line will be here. It will have experienced an angular displacement. And so it will have gone from some initial angular position theta naught to some final angular position theta. And so we say it experienced an angular displacement, delta theta, where delta theta is the final angular position minus the initial angular position. So just like we did with our linear positions. Okay. So we do have to be careful. These are all going to be in radians and not in degrees. And so we want to be able to kind of change between them in a given problem. So let's just remind ourselves of how radians work. Let's suppose that we were to rotate this thing through an angular displacement, delta theta, of 1 revolution. So we could say revolution or rotation. It's going to rotate around once. So in degrees, that would correspond to 360 degrees of rotation. And in radians, that would match up with 2 pi radians. So each revolution represents 2 pi radians. And to convert between the two, 1 radian is approximately 57 degrees. So we can switch back and forth between them. Now, at this point, I'm going to be really careful that we don't confuse the difference between angular displacement and circular movement. Because we've already done an entire unit on circular motion, such as uniform circular motion, and we've got vocabulary to talk about those things that isn't necessarily the same as what an angular motion would describe. So suppose we have a rigid rotating body, and again I'll draw this in 2 dimensions, and that this dot right here represents the axis of rotation. So this whole object is going to rotate about this point, say in the counterclockwise direction. And I were to pick two different points on this object, say point A and point B, that are drawn on the object. Now, as this thing rotates, both point A and point B will move. A will move in this direction, B will move in this direction, and they won't necessarily move the same distance as this thing rotates. So we could say that as it rotates, A and B always experience the same angular displacement, but different linear displacements. In other words, they travel through the same angle, but not necessarily the same physical distance. So if we were to kind of zoom in on that and look at that a little bit closer, we might see something like this. So if we were to draw a line from our axis of rotation, say this is point A, and this is point B, here's our axis. As this thing rotates, this whole line, this reference line, is going to rotate to a new position. And so sometime later, point A is going to be here, as this thing experiences its angular displacement, and point B is going to be here. So A has traveled a relatively small distance, and B has traveled a larger distance, though both of them have experienced a move through the same angle. So they both traveled through the same angle theta, but they've traveled different arc lengths. So we're going to use the variable s to talk about the arc length. And so we'll have an arc length for point A, and we'll have an arc length for point B, SA and SB, that are not equal to each other. Okay. So in general, an angle subtended is equal to a ratio of arc length to radius, as long as my angle is measured in radians. This is how radians work. A ratio of arc length to radius, a way of measuring the angle. So in general, I could say that these two lengths, SA, is going to be equal to RA theta, and SB is going to be equal to RB theta, where RA and RB represent the distance from the axis of rotation to where that particle is. So this dimension right here would be RA, and this dimension right here would be RB. So they both travel through the same angle theta, and yet having different radii, therefore travel through different linear displacements. So in general, we could say that arc length, S, is equal to radius r times angle theta. This is a very useful relationship to move between the linear variable and the angular variable. And we'll see this relationship of multiplying a radius by the angular variable will often be used to figure out the linear corresponding variable. So now we're going to talk about angular velocity. Just like we did for linear motion, once we could talk about where something is, we can talk about how fast it's moving. So we're not going to use the letter V. We're going to use a different set of letters, and for our angular variables, we'll be using Greek letters. So instead of X, we use theta for position. So we're going to go to the Greek alphabet, and we're going to use the Greek letter O, which doesn't look anything like the English letter O. This is the Greek letter omega, actually the last letter of the Greek alphabet. And it looks kind of like a W, a curly W. I don't know, kind of like the Wegmans W or something. And instead of traveling meters, we're going to be traveling radians. So position is measured in radians. So instead of meters per second, we have radians per second as our unit for omega. A radian is a ratio of two lengths, so it's not technically a unit. So from a dimensional standpoint, the units for angular velocity are just 1 over seconds. Okay. And the bigger this number is, the faster the thing is rotating. So we're going to see a very similar relationship. We talk about angular velocity. The average angular velocity is the rate of change of angular position. So we can say delta theta over delta t, just like linear velocity is delta x over delta t. So here's our definition of how fast something's rotating. Okay. And yeah, figuring out how far it's rotated divided by the time gives me the rate. The tricky part about angular vectors, this is a vector quantity. There's a direction in which this thing is rotating. And so, I don't know, there's a little weird math going on here. We're going to treat delta theta like a vector. Okay. Now, if we want to be precise, delta theta is not technically a vector since it's non-commutative. Commutative property of addition means you can add numbers in whatever order you want and you get the same result. So 2 plus 3 is 5 and 3 plus 2 is 5. Rotations don't work that way, and I could show that to you sometime later when we get a chance. For now, just take my word for it. Okay. So omega has a direction defined by something called the right-hand rule. And in physics, there are a number of right-hand rules that are going to be really useful and important to us. So how does the right-hand rule work for angular vectors? Let me go ahead and describe this. We'll have right-hand rule for my angular vectors. And you use your right hand. The principle is that you're going to curl your fingers of your right hand, of course. If you use your left hand, this isn't going to work. So curl fingers of right hand in the direction of rotation. So clockwise, counterclockwise, whichever the direction the body is rotating. And if you do that, then your thumb shows the direction of omega, the direction of the angular velocity. Okay. So let me show you what I mean by that. Suppose that I have a rotating object that looks something like this. I've got a bowling ball, perhaps, that's rolling down the alley. And let's say it's rolling in this direction, so the overall translational motion would be to the left, something like this. And I want to describe which direction its angular velocity is in. So to use the right hand rule, what I would do is I'd take my right hand and I would curl my fingers in the direction of the rotation. So I can either curl them clockwise or in this case counterclockwise. And then my thumb is pointing directly towards you, so it's pointing out of the drawing. So the direction of the angular velocity vector is an arrow that's coming out of the drawing. So I need a way of representing this, and the way that we show an arrow that's coming out of the drawing is with a dot, something like this. So this is the direction of omega in this case. So our convention is that if an arrow is pointing towards you, it looks something like this. And if the arrow were pointing away from us, we would represent this as an X, away from you. And it's sort of an archery thing, so that towards you would be out of the page. Page, P-A-G-E, there we go, okay. And away from you would be into the page. And so imagine you were firing an actual arrow out of a bow. If it was moving away from you, you'd see that X shape of the feathers, the fletchings as they move away from you. And if it was headed towards you, you'd be, right before you died, you'd be like, oh, I can see the point of the situation here. And that's the tip of an arrow headed towards your face. So, pleasant thought there. So in 2D, we can simplify this just to positive and negative. If we have a rotation that's counterclockwise, like this bowling ball here, so the rotation looks something like this, we're going to call this a positive rotation, rotating in the positive direction. And the main reason why that is because of my Cartesian coordinates. If I were to draw an XY axis like this, the positive Z direction would be coming out of the drawing towards us like this. So counterclockwise rotation, my thumb would be pointing in the positive direction. And a clockwise rotation is going to be the opposite. Something's rotating like this. We'll call that a rotation in the negative direction. let's look at how the right-hand rule can be used to describe the direction of rotation for an object like this. So I want to figure out the direction of its angular velocity. So let's get it spinning first. So now this object is spinning. And as we watch this wheel spin, the particles, the different parts of this wheel are moving in all different directions. So we've got some that are moving down, some to your right, some up, and some to your left. Okay. So I need to pick a direction, a common velocity vector for everything that isn't in the plane of the wheel's motion. So that leaves me with only two possibilities. Either I can have a velocity that points towards you, or a velocity that points away from you. So I'm going to use my right hand to determine this, and this is just the choice by convention. Okay, so right hand, I'm going to take the fingers of my right hand and I'm going to curl them in the direction of the rotation. Imagine like grabbing this hub here with my fingers curling this way, not this way, but in this direction. Now my thumb is going to show the direction of the angular velocity. So right now this wheel has an angular velocity that points towards you. If I were to take the wheel and spin it, I don't know, spin it like this, okay, so that it's rotating in this sort of a manner. I can do the same sort of thing by rotating my fingers in the direction that the wheel is spinning, and now the angular velocity vector points towards your right. So the last variable we're going to consider is angular acceleration. And maybe there are others, I don't really know, honestly. Maybe there's angular jerk and snap, crackle, and pop, I'm not sure. But we'll look at angular position, velocity, and acceleration just like we did in linear. So again, we're going to the Greek alphabet. This one, I don't know, is a little bit more logical. Instead of using the letter A, which we'll use for linear, we're going to use the Greek letter A, which looks kind of like a fish. Okay, this is the Greek letter alpha. It's a lowercase alpha. First letter of the Greek alphabet. Okay, so of our angular acceleration, and that's going to be the rate at which my angular velocity changes. So instead of meters per second squared, we're going to have radians per second squared. And again, since a radian is just a ratio of two lengths, technically inverse second squared is the unit for angular acceleration. Okay. So in terms of an equation, alpha is going to be equal to the rate of change of omega, change in angular velocity over the change in time. And this will yield the average angular acceleration. So the faster you change your angular velocity, the greater your acceleration is. Now, similar to linear acceleration, whether or not accelerations cause me to speed up or slow down is always a matter of whether it's with or against the velocity vector. So let's consider, for instance, say a rotating sphere, and I'll try to draw this three-dimensionally here. So got a rotating sphere like a ball, maybe a basketball spinning on somebody's finger or something like that. So we'll have an axis of rotation that goes through its center. And let's say the object is rotating something like this. Okay. So this is good practice for the right hand rule. Take a moment. Which way is this object rotating? Well, you got to use the fingers of your right hand. You got to curl them around in the direction this thing is spinning. And then your thumb is going to show you the direction of the angular velocity of this object is in this direction. So there's the direction of omega, perpendicular to the actual moving particles. The angular velocity is always going to be parallel to the axis of rotation. And so if you're spinning this as a basketball on your finger and say it's slowing down, it's beginning to lose speed, you're not pushing on it anymore, then that must mean that it's experiencing an angular acceleration against the motion. So if I were to want to slow this thing down, then I'd want the alpha vector to be the opposite direction of omega. So this angular acceleration would slow it down. And an angular acceleration that would speed it up, say you're going to spin the basketball faster and faster, maybe push on it with your other hand, you would be creating the angular acceleration in the same direction as the motion. This would speed it up. And just in case you're wondering, it's possible that I could have an angular acceleration that's neither with or against the angular velocity that doesn't make it go faster or slower, such as maybe an angular acceleration that looks something like this. Any guesses as to what that would make it do? You got it. Change direction. Going to change the direction of our rotation vector. And we'll take a look at some examples of that a little later in our unit as well. So let's do a little bit of problem solving and see how these equations can be put to use.